Welcome all of you. So we'll start our session. So we are waiting for more people to join the session. And all right, so we'll start our session. So today we are here to solve some of the assignment questions. Based on the our course molecular rearrangement and reactive intermediates in the organic synthesis, and this is our eighth session. So in this one, we are going to solve some of the problems. So before moving to the problems, so if anyone have any doubts, so we can take that doubt, and then we'll move toward the sample problems from the assignment of the eighth week course. So uh, please stop me in between if you have any doubt. So I will take the questions one by one. So here is the first question for the today's session. Uh, the question states major product form in the following reaction. So we need to identify which is the major products formed in this one. So we have given the starting material which has the methoxy substituent, the benzene ring with the methoxy substituent and the methyl substituent, and the reagent are the butyl lithium. So this butyl lithium abstract the proton. So we have the two different type of proton that are available for the abstraction. So the first one I write with the color code. So one is the green one and another one with the red one. So if you look at the two different photons, so the HA particularly and the HB, so among these two, the the proton which is the HB proton, which is sterically hindered because of this methyl group. So methyl groups, which if I just elaborate the structure of this methyl, so it will be it has the three hydrogens, right? So this will be the bulkier group, not that bulkier, but still it make the some steric repulsion to abstract the proton by butyl lithium. So we have the reagent butyl lithium. So the butyl lithium abstract the proton. So I'll just write in this form. So this will be the terminal carbon will be the C negative, and the lithium ion will be the positive. So this is a strong base, and it has ability to abstract the proton. And because of this methyl group, it direct the ortholithiation. That is the intermediate form while abstracting the proton, which stabilized by this methoxy group. So this will be, let's say, uh, the structure which has the proton here, and the chain. Uh, so this C negative and the lithium. So this lithium basically get coordinated with the oxygen. So here, which has the OMe, so that will be the remain same. And this lithium, so this part had some polarization between the towards the oxygen, because the this lithium is the Li positive and C negative, right? So this positively cation get the stability uh, to near the oxygen atom, and this C negative, that's the part of the butyl chain negative which abstract the proton. So this proton is getting abstracted, and we get the here. So once this proton abstracted here, there is it forms a negative charge, and which is then stabilized by the lithium positive, right? And further, upon treatment with this, we have the electrophile C double bond O. That's the CO2. So which get so this negative charge attack on this CO2. So it is source of electrophile, and we get the here OMe will be remain as it is. The methyl group will be remain as it is, and here the C double bond O negative is formed, and upon workup, or we call it as a H plus, so it gives the acid group. So which product is formed? So the final product in this reaction is the this one. OH. So option C is the correct option here in this first question. So any doubt in this question? All right. So if you don't have that, I will move toward the next question. So this is simple, the question of the ortholithiation. Uh, so you can refer this the mechanism. It is given. So you can write down from here. And in this question, I also explain why this Hb proton is not get abstracted. So the reason behind, so it has some sort of steric crowd. That's why this Hb proton is not getting abstracted. So this is the major product, and there will be a minor one will be, and there are also some chances of formation of the product like this. Like this. So these are all minor or trace. It will form in the trace amount. So any doubt in this question? We'll move to the next question. Next question is also based on the similar approach. So in this question, so we need to identify the major product formed in the following reaction, and we have a starting material. So this is the pyridine substituted pyridine, And if you look at the structure, which has the basically two bromo substituent, both are the at the meta position to the nitrogen, and one is the methoxy substituent at the ortho. But if you look at the difference between the two bromo, these two bromo groups, so the basic difference is the OMe at the ortho position to the HB. So therefore, the butyl lithium is preferably extract the sorry the from the lithiation at this position. So because this OMe stabilize this lithiation, so there will be some sort of ortholithiation type of stability get in for this intermediate, and then further the addition of this PCHO, so that will be the same, that's the source of electrophile. So this bromo will be remain as it is, this nitrogen, this OMe, and here it attacks on the if you elaborate the structure of this PCHO, so that will be the benzene ring with the double bond OH. So this negative charge attacks on this position. So we get here O Li, then the proton will be remain as it is, and here there will be a phenyl ring. So I will write in the short form, then and then obviously upon workup it will get converted into the so OLi, so that will be converted into OH, right? So which one is the product here? So this A is the major product here. Why not the B product? This will be the minor. This is because this ortholithiation stabilization is not possible, which is not possible when the bromo is getting substituted with the lithium. So the product A is the major product here, and other products are these are obviously the wrong products. So you can also see the mechanism, which also uh, mention the same stabilization due to. And if you just go by another way, like the another bromo, it is getting replaced by the lithium. So that time, so what the products form? So this will be the bromo, and this is the OMe, and here the negatively charged come, or here the and lithium plus. So they're not stable compared to this is the intermediate A, which got stability due to the ortholithiation. So this small thing you need to always keep remember while you are approaching to solve such problems, right? So any doubt up to here? So I will move toward the next question. So this is the third question, and which is again similar. So major product formed in the following reaction, we have given the alpha beta unsaturated ketone, and the substituent, it has the substitution, the phenyl substituent, and we have added the methyl copper lithium complex. So always remember when you add the copper mhm, mm, organocuprate, it always acts as a soft nucleophile. It doesn't. It is a soft nucleophile, and it attacks by the on the fourth position. So the attack takes place on the fourth position. So what it gives? It will give the. So here there will be a phenyl and the methyl that's come from the organocuprate. So that goes, and here O TMS getting formed. So O negative form that converted to OTMS. Then we have added, we have the pH C double bond O H. That's the again the so this will be the again the source of electrophile. So once this complex form, so the lone pair on the oxygen goes to down, and through this it attacks on this pH double bond O H. So attacks here. So what the product form upon this one? So we get this uh, O, this keto back. Further here there will be a O H, then there is pH. So here pH is there, and here the methyl, which is from the organonucleotide. So this is product form in this reaction. So we'll neglect this wrong option because they have shown the attack here and also other options. So this methyl attack here, that's again the wrong. So option B is the correct option here. So I hope you understand this question. So you can refer this reaction mechanism. This is a stepwise manner. So the same one that I have explained. So this methyl lithium attacks at this position, right? And this OLI complex form, which is then converted into the OTMS, right? And further, when it attacks on this benzaldehyde, this goes the lone pair goes here, and through this position, it attacks on this center. So this is the part of this benzaldehyde, right? And then upon workup, it get converted into the this anion after the proton. So it converted into alcohol, and this O TMS will be get cleaved upon workup oil hydrolysis. So this is the product. So the option B is the correct option here. So these are the some simple questions. So in each question, the concept is very similar. So basically, only the where we need to identify which intermediate is stable among the available one. So here also the same approach we have used to solve this question. So you can note down from this slide. So I will erase all the unwanted this. Right. And you should you can note from this one now. We have the similar next question, and but here the small difference. So in the earlier one, we have added the copper one organoequivalent. Here we have the grignard, that's the magnesium based complex. And always remember this magnesium based the grignard reagent, they are strong. They always attack on the carbonyl carbon. So upon addition uh, of this CH3 negative and Mg, we are positive. This CH3 negative uh, attack directly on this carbonyl center, and we get the intermediate. So CH3 O CPR, and further upon hydrolysis, upon workup, so it get converted into the OH, and here the methyl from this Grignard reagent, and we have the methyl, the substituent that already in the already in the starting material. That's the CH3. So any doubt in this question? So now I'm asking one question for you. So what if instead of this copper, if we add the if instead of this magnesium MgBr, if we add the if we add the CH3 Cu CH3 twice Cu complex or CSU Cu Br, that's the complex the reagent from us. Organic cuprate. So if you add the organic cuprate, so what will happen? So in this case, on the same one, so what the product will get? So we get this product. Yes, the double bond will be remain as it is. Here there will be the proton, and here there will be the upcoming nucleophile and the CS will remain. So this missile will be from uh, this copper. This copper, because of this copper, it will be acts as a soft nucleophile. So this some type of similar type of question we have also seen in the last week also. You can refer the mechanism from here. Uh, in case of the magnesium, so the addition will be the 1-2 fashion. But in case of the copper, in case of the copper, that will be some different manner. That's one per fashion. So all right. So up to here is okay. Now we'll move toward the some different type of question. So I hope this is also another one question. You can able to solve this one. So this is the fifth question, and which has we have the fluoro version. Now we have if you add the butyl lithium, so what will the product in this case? So in this case, the as we seen earlier some example, if we have such group with the OMe and with the either with the bromo with the same butyl lithium. So that product we have already seen earlier. But now here, if you look at the fluoro version, if you have the fluoro and the methoxy at this substituent, so what will happen in this case? The the proton at the ortho to the methoxy get abstracted. It forms the lithiated complex, and this fluoro will remain as it is. And upon the electrophilation that CO2, so it gives the carbonyl acid at that position. So we have already seen in detail this reaction mechanism. So I'm not going to explain completely. So you can refer the previous examples. So this is the product form in this reaction. So option A is the correct option here. So you can refer this mechanism. So that's the so I have shown the same one similar mechanism. Now this was the some questions from the based on the butyl lithium. So I will take some some different examples. So which is based on the week 9. So week 9 problems. So week 9 basically based on the reducing agents like LiBH4, NaBH4 and ZnVH4. Zinc borohydride, I think we have that also we have seen, and yeah, ZnBH4 twice. So ZnBH4 twice. So this type of, and also along with this, the BH3 THF. So this sort of problems, sorry, reducing agents uh, for reduction of the carbonyl compounds or for reduction of the different type of whether it is aldehyde, ketone, or carbonic acid, or ester, or acyl. So on this type of substrate, we have studied the role of these such reducing agents. So that sort of problems will going to start. So that problem basically based on the week 9, not from the week 8. So it will be help you to solve some advanced in I mean uh, instead of in the next week. I'm taking this problem to this week only, and the next week we'll see some more problems overall based on the week 8, week 9, or week 10. So we'll be ahead of this syllabus. So this was up to the problems from the week 8, and the next problem, which is based on the week 9 problem. So I'm writing in the here. So here also. So the first problem, and which is based on the reducing agent. So LiAlH4, addition of the this LiAlH4 reducing agent on the substrate. So this is the bridgehead position which is directing upward. You can see here. So now how this LiLH4 is going to act, and whether this hydroxy will be equatorial or it will be axial. So depending upon this bulkiness of the reagent, so it will be equatorial axial. So I will explain one mechanism in the detail. So the steric cloud of this LiAlH4 cannot attack from the below side. Why cannot attack from the below side? If you look at this the structure, so which has the, so this is the carbonyl group, and if you look at the hydrogen substituted hydrogens, so that will be directing downward, and so this axial hydrogens. So again here also there will be one hydrogen directing downward and one is upward. And again, here there is one another hydrogen. So because of this, sorry, this hydrogen directing downward. there will be a steric repulsion. So there will be steric repulsion. So if LiALH4 try to attack from the downside, well, that's not feasible. So we can see here. So attack from the downside. So that will be uh, prohibited by steric repulsion. Instead of repulsion, the steric crowding will be the correct terminology. Repulsion, if we use the whether it is lone pair and the negatively charged repulsion, that will be a that time we can use that word as a repulsion. But here, due to the steric crowding, will be the best word. And due to the steric crowding, the hydride attack on the downside will be the difficult. So the hydride attack on the upside is more favorable here. So when the hydride minus attack on the above side, this hydrogen will be comes on the here on the equatorial position, and the hydroxy will be on the downside at the endo position, the hydride on the exo position. So exo hydrogen will be the there, and endo hydroxy group will be the major product. So so this was the reason. So what product will you get in this question? The endo one, endo hydroxy group will be in the product. So that's the product. We get the major product. And this obviously the not correct products. And this one formed by the attack from the downside, but the downside attack is not preferred due to the steric crowding. Here there is another question, and which is based on the reduction of the double bond by uh, not reduction. So that's the first step is the reduction followed by the H2O2 addition. So we have added the BD3 THF. So similar to BH3 THF. So instead of a hydrogen, there is a deuterium. So mechanism will be very similar. So in this case, what will happen? So upon double bond, so if you have the double bond, the starting material like this. So here let's say methyl, and here double bond. So BH3 will be, so this is the H, and here there is the B. The remaining H will be the remain here, and so this hydride can attack here, or also, and boron attack. So once the hydride attack here, so this bond goes here. So like this way, and once this attack will be on the syn side. So we get a product. So in which this is the methyl will be in the, let's say, the downside, whether it is downside or upside, whatever it is. So just write in the syn fashion. So this methyl will be, so if I writing this methyl on the syn side, so there was a hydrogen. So that hydrogen again will be there, this hydrogen. Now the BH3 and the, so the hydride from the BH3 and the VH this complex will be the syn fashion. Now we have added the H2O2. So once this H2O2 attack the OH negative attacks initially here, so that form the OH complex, and further the entire group will be replaced by the hydride, sorry, the hydroxy group. So here we'll get the product in which this CH3 will be upside. There is another one hydrogen which is again upside. So this hydrogen, so it will be upside, and the hydride that is this hydrogen is below, and again there is the hydroxyl which is again the below. So this is product formed in the reaction, that is which has the hydride and this hydroxyl in the syn side, and this methyl and hydroxy will be on the anti, right? So if you look at the correct mechanism here, so you can see in the same manner, instead of that hydrogen, here just the difference is the deuterium. So that's just a isotope of hydrogen. So the mechanism will be the same, right? So that's the BH3. So this is the BH3 part or the BD3 part. So this BD3 will be remain on the syn side, and then H2O2 addition to this intermediate form, we get the this OH and the D on the syn side. So what will be the correct option in the correct option? So here this methyl and hydroxy they have written on the syn side. That's the wrong option. Here methyl and hydroxide they have shown on the syn side. That's again wrong option. And here, so here the attack will be a attack they have shown, which is incorrect one, because the addition of this hydride ion will be takes place on the carbon which is substituted by more number of carbon atom. So that's the Marconi-Crox rule, addition takes place by that manner. So hydride, that's the negative one. So which is it should be attack at this position, and the positive charge electrophile will be on this position. So therefore, this type of addition will be again the wrong one. So in this one, option C is the correct option. You can see the deuterium and the hydroxide will be on the same side, and the methyl and hydrogen that will be on the again the same side, and relatively the methyl and hydroxide group will be on the anti side, right? So this was the mechanism, and you can note down from this slide. Another very similar question. Only thing here is the BH3. In earlier case, there was the BD3. The same, the mechanism will be the same. So in this case, you can directly write down the product. So here, the hydrogen will be here, and the hydroxide will be here. And again, the if you look at the stereochemistry, because on the top side there is a steric bulkiness, the BH3 will takes place attack on the downside. So I'll directly write down the product. So these are the part from the starting, and so this methyl will be directing upward, and here there was a double bond. So that double bond now get converted into the single bond, and therefore if you look at these hydride that will be here, and initially it will form the BH3 and then followed by the methyl addition. So that will be again, sorry, hydroxide. So that will be here. There are hydrogen. Right. So this is the product form. So This is the wrong because there is a steric crowding on the top side. So that's why this is the wrong product. Again, the hydroxide that addition they have shown incorrectly. This hydroxide and methyl group they have shown seen. So that's the wrong one. So this hydroxide and the new hydrogen is on the syn side. That's the correct one. And methyl on the top side. But if you look at the OH, that the OH position of this OH is incorrect. And therefore this is wrong. Now we have the methyl and this group that the syn side, basically the steric, the attack takes place from the bottom side. That's why the hydride on the bottom side, the hydroxide group on the again the same bottom side. So that's the correct product. Correct product. H is the correct product. This was the same mechanism. You can refer for the another question, this question also. So any doubt in this question? All right, we'll move toward the next question. So, which is again based on the reagent combination. So here, in this question, we have given the two different reagent, namely the lithium borohydride and the zinc borohydride. So in this case, what will be the uh, impact of this reagent on the substrate? We have in the substrate there is a carboxylic acid group. So that's the A first position. So this is first reactive site. The another one is the keto group. That's the second. One is the ester. So it is third, and the fourth one is the amide. So in the same starting material, we have four different type of functional group, and we need to identify what reagent combination gives the this A and B product. So if you look at the A product, what happens in the A product? There is a reduction of ketonic group. Also, there is also reduction of ester group, but acid and amide group remain unaffected. So, what's the reagent combination used for this one? So, ester is reduced, sorry, ester and the ketone is reduced. So, obviously, this will be the LiAlH4. But if you look at the next product, the B product, which has the reduction of acid group, reduction of keto group, and the reduction of ester group, along with reduction of amide group. So all four groups are reduced. So therefore, this is the work of ZnBH4. So ZnBH4 is very strong reducing agent. It can reduce the acid, keto, ester, amide, all four functional group present in the starting material. So option B is the correct option here. So you can, oh, sorry. So no, that's again, yeah, this is the ALLH4, and we also have the LiBH4 also, because it's also reduced the acid group. So that's impossible with the ZnBH4. So here LiBH4 is the correct one, not ZnBH4. LiBH4. So the first one is the, that's the A is the acid reduction, and this is, so in this case you need to identify so here in the answer you can see LiLH4 reduce the ester group. Also, it has reduced the ketone group, LiLH4. LiLH4 also reduce the acid group and the amide groups. So with this is the LiALH4. The next one is the ester group is reduced to alcohol. The keto group reduced to again alcohol. Carboxylic acid group remains same, and amide group remains same. So it is LiBH4. Right. The next question is the on the major product formed in the following reaction, and we have given the starting, which has the chloro substituent on the carbon and the bpene substituent. So addition of methyl magnesium bromide on this compound, what will happen? So this will be, if I just elaborate the structure of this one, so it will be B pinacaloto borane, right? So this is the structure, and there is again one hydrogen, and addition of this ME methyl magnesium bromide. So that's the negatively charged methyl, which attacks on this electrophilic boron. So it will give the ClHCl, and this boron, this O, this boron will be negatively charged now. And then once this intermediate form, further this methyl migrate here, and this chloro get eliminated. So we get the chloro, so this hydrogen ribbon as it is, this methyl chloro one chloro. There, this is the another methyl from the methyl magnesium bromide, and this pinacolto borane group will be remain as it is in the final product. So this is uh, the reaction happens at the this starting material, this because of the 1-2 migration. So this step is called as a 1-2 migration of the methyl, right? So this was the product. So product one, sorry, which one is the product? C product is the major product in this case. Another question is, write down the correct order of ketone reducing ability among the following borohydrates. So we have given the NaBH4, ZnBH4, and LiBH4. So this ketone reduction ability is odd. The chelating order depends upon the chelating order of these anions. So sodium borohydride that has the sodium plus anion, Zinc borohydride has the Zn plus Zn 2 plus anion, sorry, ion, and lithium borohydride has the Li plus ion. So zinc 2 plus has the more ability for the chelating with the oxygen, then the lithium plus, and then the sodium plus. So therefore, the carbon make more electrophilic, and then for the order will be in the same manner of this chelating ability. So it will be first will be the B, that's the zinc. Then there will be the lithium, that's the option C. The B, then C, and then A. So option B is the correct option here. Next question on the we have the starting material aldehyde plus we have the boronic acid and the reaction in the THF at room temperature under argon atmosphere. So what will happen to this in this reaction? So we have the aldehyde. So if you look at the reaction mechanism of this reaction, it will be in this manner. So we have the boronic acid. So that will be and that 2 alpha beta unsaturated boronic acid, right? So this is the part of boronic acid. Further, we have the aldehyde. So that aldehyde will be coordinate with the boron atom of the boronic acid. And here, so this is how the coordination takes place. The oxygen boron and further the alkene part with the carbonyl center and further. So the this bond shift to here. So the oxygen atom attacks on the boron. So the carbon boron bond get cleaves to form double bond at this position, and this further this alkene attacks on the carbon carbon. So this is the newly formed bond, and once this intermediate is formed, so upon hydrolysis, this will be this OBA oxygen boron bond get cleaved and get the formation of alcohol here. So we get the product. So like this. That's from the starting. We have the those R group. So that's the remain same. So what is the product here? So product A is the correct here, correct option here. Right. So any doubt in this question? So basically, this reaction goes to chair-like transition state and sequential oxidation, uh, forming alcohol as a product. Another question in the same manner, though we have the boric acid. Uh, Not the same manner. Here it is some sort of coupling reaction. So if you look at the starting material, which is a we have the bromo compound and vinyl bromide as starting material, followed by the boronic acid, phenyl boronic acid, 4-methoxyphenyl boronic acid, in place of palladium PPH3, 4 as a catalyst and base as a KOH, solvent DCM. So what is happened? What will be the product here? So in this case, this is the basically Suzuki type of coupling or Suzuki coupling. So in this case, this this is the part of the starting A, and we have the starting B. So this is the start of starting B. So A product is getting formed. So only here, this bromo position, this carbon-carbon bond formation takes place by Suzuki coupling reaction. You can refer the mechanism of Suzuki coupling reaction. So you will get the answer for this one. So these are why these are the incorrect one. So in this case, they have changed the stereochemistry. Uh, so here they have written cis. So that's if you look at the attachment here, it is a trans. So the cis one is the incorrect option. Here they have added at the some different position. So that's again the wrong one. And you can refer this mechanism of the Suzuki coupling reaction. So this is palladium catalyzed Suzuki coupling reaction forming carbon-carbon bond. This reaction proceeds through the mechanism involved. First step is the uh, so on this first this is the first step. First step is oxidative addition. So this is the first step. Oxidative addition steps takes place. So the oxidative addition means palladium is added between the carbon and the bromide bond. So this is the oxidative addition followed by the ligand exchange. So basically, uh, so palladium 2 plus this bromo version in place of the base, the bromide get eliminated and of OH is attack on the palladium. Further, here we have the boronic acid, which is activated by the base, so it forms the boronate. So that's the negatively charged boron is getting formed. So the third step takes place in the transmetallation. So the carbon and the boron bond get cleaved and the palladium inserted in between. So there will be a phenyl ring and here there is a boron. So that again get eliminated from this on the from the palladium species and then followed by the reductive elimination step. So the reductive elimination gives the final product. So this is how the product form. So this is the standard mechanism of the Suzuki coupling reaction. So you can refer this mechanism to solve this earlier question. And by this mechanism, the option A is the correct option. So refer this mechanism. You need note down this mechanism. If you have any doubt, please let me know. So the four steps are important. First one is oxidative addition. Second one is the ligand exchange with the base. Third one is the transmetallation, and fourth one is the reductive elimination. These are the four steps involved in the generally most of type of such palladium catalyzed coupling reactions. whether it is Suzuki coupling reaction or Higg coupling reaction or Buchwald coupling. Uh, that's basically the basic mechanism is the similar. We have the next question. So before going to next question, if you have any doubt in this question, please let me know. I will wait for some time here. All right. So we'll move to the next question, which is again based on the reduction type of reaction. We have the starting material, which has the one is the ketone group and one is the aldehyde group. And if you have ordered only one equivalent of NaBH3CN, sodium cyanoborohydride, then what will be the product? So if you look at this reactivity of sodium cyanoborohydride, uh, so this is the sodium cyanoborohydride acts as a nucleophilic hydride source. That's obviously the source of reduction agent. And this nucleophilic hydride donor react with the more electron deficient center. And in this scenario, so we have two functional groups are present. One is the aldehyde group, which contain more electron deficient carbon center compared to the ketone group. So you have the aldehyde groups and the same, let's say you have the ketone group. So because of this inductive effect plus I inductive effect, this center will be less deficient compared to the aldehyde center. So here only uh, two inductive effect, here only one inductive effect. So therefore, this is the less, sorry, this is more electron deficient center, and therefore this uh, NaBH3CN react preferably with the aldehyde one. So what will the product here? So only aldehyde get reacted. So because we had only one equivalent of the sodium cyanoborohydride, so the aldehyde center only get reduced. And again, the double bond will be remain unaffected with the in case of this sodium cyanoborohydride reduction. Next question we have the nitro group and we have added LiAlH4. So this nitro group in terms of LiAlH4 get converted into the amine, corresponding amine. The aromatic system will be remain unaffected with the LiAlH4. Only nitro group getting reduced. So nitro group reduced to the amine. So that's the option A is the correct option here. And next question based on the BH3THF type of reduction followed by the uh, H2HCl workup. So here BH3THF specially particularly only react with the acid, not with the ester. So we get the reduction of the acid as a product, and it reduce the added acid completely to the alcohol, not stop in between to aldehyde or ketose step. So this reduction of this acid to alcohol takes place in presence of this BH3THF reagent. The ester group will remain unaffected. So this was the A option is the correct option here. So the BH3THF selectively reduce carbonic acid group over the acyl chloride group or the ester group. Here the another question based on the major product formed in the following reaction, and again here we have the ester and we have added the diol H. That's the reducing agent again. And this diol H reduce this So this is the mechanism. So basically, it's the source of hydride. So this hydride attacks at this position. So once this hydride attack at this position, so this is the hydride. It form Al. This form Al complex with the Al, and then upon so here upon hydrolysis or upon workup, this complex breaks to corresponding alcohol. Sorry, it will be goes here, and this bond will opens. So I will just check whether this one is the correct one or not. Right. So it will be goes to. So once this intermediate is formed, so this H2 attacks on the Al on the aluminum, and this bond between Al and O get five membrane, not six membrane. So here the O negative form, so that bond comes here. This bond get opens, and which is then so here it will be double on O H, and here it will be O H. Favoring women as it is. So this was the product. So option B is the product correct option here. So basically only the reduction of this ester group takes place. So reduction, so it gives the aldehyde at this position, and this ring opening will lead to the formation of alcohol at the bottom center, bottom part of this product. Option B is the correct option here. So any doubt in this question? All right, if you don't have any doubt, so we can stop here for today. I will just check the chat box if someone put any doubt. And in the next video, we'll again see some problem based on the some from the week 9 and the week 10. So please let me know if you have any doubt. So this is what we have seen today. We have seen some question based on the butyl lithium and ortholithiation type of reaction on the aromatic systems. There some seen some problem based on the selectivity on the two different position. Again, we have seen the stabilization, how the stable ortho-lithiated complex leads to the formation of major product. So in the next question, again, we have seen the organocuprate addition on the alpha beta unsaturated keto compounds. Then again, we have seen the addition of the grignard on alpha beta unsaturated compound. And then we move to the on the reducing agent, which is basically the the topics of the week 9 uh, videos of this our course, molecular rearrangement and reactive intermediates in the organic synthesis. And then we have seen the addition of the LiAlH4 on the bridged or the such such compounds which have the steady crowding on one side, and so which leads to formation of endo substituted product, as you can see here. So this was the mechanism that we have seen. The steady crowding leads to the unstable intermediate formation, and unfavorable transition state. Then we have seen the addition of the BH3 THF, so BH3 on the double bond, followed by the attack of the H2O2. So this was the product, some problems, and some example with the already steric center in the starting. So there will be a steric selectivity and again regio selective. Both concepts are covered in the same question. Here we have seen the we have the four functional group on the same molecule, and the the reducing agent reagent combination to form such A and B product that we have studied here. And then similar question based on the some question based on the bisphenol diborane starting material, which has the alpha dichloro substituent. So this green and on which we have seen the addition of the Grignard reagent. So here there was 1,2 migration step take place. So the chloro group will be substituted by the methyl. Then the reactivity order of these uh, sodium borohydride, zinc borohydride, and lithium borohydride toward the keto compounds that are covered, and some intermediates, some question based on the sequential oxidation of this alcohol. Sorry, oxidation of this. Sorry, the reduction of this carbonyl group by using the boronic acid that we have seen. Here, one example of the Suzuki coupling reaction also covered with the mechanism. You can see here the reaction mechanism. You can note down from this slide, and some question based on the reduction of the nitro group and all. So this was the problem, some problems for today. So I will upload this slide and video also on the YouTube. So the slide will be on the drive link that probably we may have. So see you in the next week on next Tuesday.